Hello, everyone. Welcome to this chapter about rules of differentiation, where the main goal will be to be able to compute the derivative of a function. Of course, we're also going to do a lot of application, but the most important application, the most powerful one, will be how to build the graph of a function using derivatives. In particular, we'll be using the sign table of the first and the second derivative. So very, very important stuff. I want to start with a very important remark about this chapter. So far, if you have a function that is defined by a graph, you should be comfortable. So if a function is given as a graph, you should be able to tell me, where is this function increasing? Where is this function decreasing? If the function has any local or global minimum or maximum, you should be able to talk about concavity for this function defined by a graph. So you should be able to tell me, where is the function concave up or concave down? And if there's any point on the graph where we have a change of concavity, also known as an inflection point, you should be able to tell me where on the graph there's inflection point. But this is all for functions that are defined by a graph. But what if the function that we start with is given by a formula? How do you compute all of these concepts? So chapter 2 is all about finding a way to compute all of these ideas that you're comfortable with visually so far. All right, first section, the informal definition of the derivative. Here, be careful. Even if I'm saying the informal definition, it is an important definition. You need to really have a good understanding of what is the derivative visually if you want to be able to use it algebraically later. So, definition. If you start with a function f of x and a point in the domain of your function, intuitively, the derivative of f of x at that point x equal a, where we will denote this by f prime of a. So we're using f because it's a function f. We're using in bracket a because we're at x equal a. And the prime notation, that little slash there next to the f at the top right, it's because we're talking about the slope of the tangent line of f of x at that point. So that notation is really faithful to the function f and the point a. So what is that tangent line of that function? So I have two examples for you. I have one example for one function that is increasing, and I have another function where the graph of that function is decreasing. So for example, on the first graph, suppose I have a point A in the domain. I am on the graph of my function. The tangent line is basically a linear function, so it's a straight line that is such that it hits that function only at that point. I don't want to be too violent, but it's as if you were taking a stick and you were like slapping that function at that point A, the way it would land on the graph would be the tangent line. So here, f prime for that function f of x at x equal a is really that slope. So if we find that slope, that's f prime at a, the slope of this tangent line. Another way to explain the tangent line, there's a lot of different ways, of course, but if you don't like that aggressive way of defining it like I just did, you could be thinking about the function f of x as a road, let's say on a winter day. And if you're driving on that road, let's say you're coming from the left and you're driving on that road, and suppose that once you reach that point A, you lose control and your tires are no longer gripping the ground, your trajectory would be a straight line. So this could happen if you come from the left, but in a similar fashion, if let's say you were driving on the road given by the graph of x, f of x from the right of A, and then suppose once you arrive at A, you lose control, then your trajectory would be a straight line, and that straight line is intuitively the tangent line of the function f of x at a. And one very important remark here is that you can see that this function is increasing. And actually, there's this very tight connection between the slope of the tangent line and that intuition behind increasing and decreasing. And this is the relationship. Here we can see that f prime, the slope, is going to be positive. This is an increasing function for the slope here. So the m would be positive, and this will always imply that f of x is, just a second, technical difficulties. So this would imply that f of x is increasing at x equal a. So if we have that tangent line and we have that slope, if the slope is positive, so if the slope is positive, for sure, at that point, for sure, the function f of x is increasing at that point. And I have another example for a function where f of x is decreasing at a. So again here, if you look at this graph and you look at the output at a, suppose you are coming from the left side, you're driving on that road, and then you're losing control, your trajectory would be a straight line. So if you're coming from the left, or if you're coming from the right and you reach a point A, you would lose control and then follow that linear trajectory. Or if you're a violent person, if you're taking a stick and you're slapping that function at that point A, the result or the end position of your stick, your straight stick, would be exactly where, intuitively speaking, the tangent line is for that function at that point. And remember, so the goal is to talk about the slope of that line, and that slope is f prime. So f for the function f at a, because we're at a, it's not the same slope depending on where you are on the graph of the function f of x. And the prime, that little dash, is really for that straight line. And here again, another very important link between that slope and what's going on with that function. Here we have f prime of a is negative, and this will always imply that the function f of x is decreasing. So it's decreasing at x equal a. So basically what I'm trying to do here is make this connection with something that you're comfortable with. You should be able to tell me if you have the graph of a function, if it's going up or down. Now I'm giving you another visual definition for the slope of the tangent line, and I'm making that little connection that will be very important, because even, and this will be a remark here, even if the idea is very intuitive. So here for my remark, just a second here. So here for my remark. So very important remark. So even if this idea, this slope of the tangent line, should be fairly intuitive, how do you define this formally, and how do you compute this in order to get an exact value? Because the goal will be to turn these notions that you are familiar with visually into a computation. And the reason why we're talking about the slope of the tangent line for a function f of x at x equal a is because that definition is something that we can compute on. Like if you look at increasing, decreasing, and etc., all these notions are nice to describe a function, but we want to compute these things, and the notion of slope of a tangent line is something that we can compute thanks to the computations behind computing derivatives. All right, so for that small section, that's it. Let's move to the next one. In this next section, we're going to make this connection between the following visual ideas. When is a function increasing? When is a function decreasing? When does a function has a local minimum or maximum? and when is a function discontinuous. And the connection will be with the slope of the tangent line of the function f of x at x equal a. So everything is still very, very visual, not just very, very visual. It's only visual. And I call this section critical points because so far, and I've made this little summary into a theorem, if you start with a function f of x at x equal a, and a is a point in the domain of your function, if the slope of f of x at a is strictly positive, then the function is increasing at x equal a. If the slope of the tangent line of the function f of x at x equal a is strictly negative, then the function is decreasing. So that's the first connection. We have this very nice connection between increasing and decreasing and the sign of the slope of the tangent line of the function f of x at a point. But then the natural question is the following. What happens if f prime is 0 or if there's no tangent line, also known as f prime is undefined or does not exist? Those points are so important that they have their own little definition. So here, if you start with a function f at x equal a point in the domain of your function f of x, then we say that this point is a critical point if it satisfies one of the following two conditions. If the slope of the tangent line is 0 at x equal a, or if f prime at a is 0, then it's a critical point. Or if there's no tangent line, so if there's no way you can figure out the slope at that point for different reasons, then we say that f prime is undefined or does not exist. That's also an example of a critical point. But remember, the point A needs to be in the domain of your function. So the way you should be able to understand critical points is first, again, visually. So the first remark here is what happens if you have a critical point of the form f prime equal to 0. Where are they on the graph of your function? Well, if you have any point on the graph where the slope of the tangent line is an horizontal line, because remember, what does it mean for a linear function to have a slope of 0? It means that you're dealing with a constant function, and a constant function is an horizontal line. So if you have a graph where on the graph you have points where the slope of the tangent line is horizontal, like here, for example, on my graph, I have 2 points, C and D, where the slope of the tangent line is an horizontal line, and visually you can see these points fairly quickly by looking at where does my function have top of round mountains or maybe bottom of round lake. So if you see any top of mountains or any bottom of round lakes, these are examples of points on the graph where f prime is 0. And we are really talking about round points. So that's for f prime equal to 0. And you can see in this case, those two examples are also local minimum and local maximum. So for C and D respectively. But these are not the only cases. You can have horizontal slope that does not correspond to a min or a max. But then the other one that you should be able to find visually very quickly. So my next visual remark, what happens when f prime does not exist? Well, the best way to find visually those critical points where f prime does not exist is by trying to find one of those three cases. The first case, if you see any corner, any pointy part on your graph, like my first example here, I have like a pointy part, then there's no tangent line. One way to think about this is that if you are looking at that pointy part of the graph, if you're, for example, if you're coming from the left and you're driving, you're on the road, you're coming from the left, as you approach A, if you lose your grip, you would go in one direction. But if you go from the other direction and you're approaching A, then what you're going to do is you're going to also lose control and you're also going to follow a tangent line, but that line is not going to be the same. So anyway, so if you see any corner, so any pointy part, there's no tangent line. So f prime does not exist, or f prime is undefined. So you can write here f prime undefined if you have a corner. As soon as you have a point where the function is not continuous, automatically, and at this point, you should be more comfortable with that. So if you see any point where the function is not continuous, any point in the domain where the function is not continuous, then f prime is not defined. Again, you can see this if you're coming from the left or from the right, you're going to be following tangent lines that are not going to be the same. And then the last case, the case where it's a bit trickier to see, those are the vertical tangent. Be careful, not vertical asymptotes here, vertical tangent. So if you have any point on the graph where the slope of the tangent line is vertical, and the vertical line is not a function, there is no slope for a vertical line, then f prime is also undefined in that case. So if you have like vertical tangent on your graph, your function does not have a slope for its, there's no slope for its tangent line. So we say that f prime does not exist. So those are the three typical ways to visualize points on the graph where there's no derivative. So corners, discontinuous, or vertical tangent. So if you see any part of your graph that looks like one of those three cases, then f prime does not exist. Let's do an example together. So again, in this section, in the first two sections of this chapter, everything is still visual. If I give you the graph of a function, you should be able to tell me when is f prime positive, negative, where is it 0, or where is it undefined. Very, very important to understand that these things are still visual. But the biggest advantage of using slope of the tangent line is because we're going to be able to compute this soon. All right, so here's an example defined visually. So we have a function that is defined everywhere. So the first thing we're going to do together is find the critical points of that function, and then we'll find where is f prime strictly positive and where is f prime strictly negative. So always start with the critical points. So I think they're the easier points to find. And then in between critical points, your f prime is either going to be strictly positive or strictly negative, which will correspond to where is your function f increasing or decreasing. So what about critical points? So here I will start by trying to find where is f prime equal to 0. And I can see that there's only one point at 0.8 here where we have the top of a round mountain. So in other words, my tangent line is horizontal. So at x equals 0.8, here I'm writing 0.8. Is it 0.8 or 0.9? As long as you pick a number that makes sense. So here at 0.8, my function f prime, the slope of my tangent line at that point is horizontal. So f prime is 0. And it's the only point like that where we have an horizontal tangent. What about f prime does not exist or undefined? Let's find first, let's say, where the function is not continuous. I see one point here at -1. My function is not continuous because the left and the right limit are not the same. So at -1, we have a point where f prime does not exist. And here I just want to give the reason. So here at x equal -1, the function is discontinuous. That's the only point on this function where the function is not continuous. So that's the only point where we have f prime undefined. So it's a critical point because it is defined at -1. We have an output, so we have a full dot. So it is indeed a critical point. And do we have a corner? Yes, I see a corner at 2. So at 2, we have a pointy part. So at x equal 2. So at x equal 2, we have another critical point. So at x equal 2, because our graph has a corner. And that's the only pointy part. There's no other corner or pointy part of my graph, so there's no other critical points of that form. And sadly, for that example, we don't have any point on the graph where the tangent is vertical, so we're done. So we don't have a critical point of the form f prime is undefined because the tangent is vertical. Normally, we like to do all three types when we test you, just to let you know. And then what we're going to do is in between, we're going to decide if the function is increasing or decreasing to check if we have f prime positive or negative. So it's essentially, so if you're not a critical point, it's because either f prime is positive or negative, which will imply that it's increasing or decreasing. So in between critical points, so my first interval, so my first critical point, the smallest critical point is -1. So what's happening before -1? So before -1, my function is going up. If you pick any point on that interval, so if you pick any point on that interval between minus infinity and -1, I have an example here in green for you. So if you look at your graph here, I have an example right there, and you can see that the tangent is a line with a positive slope, so f prime is positive. Now, between the next two critical points, so between -1 and 0.8, my graph is again going up. It's again increasing. So we have another interval. So we have another interval where f prime is positive. So union -1 to 0.8. And then between 0.8 and 2, oh no, my graph is going down. So if you pick any point, so here I have an example of a point that I drew for you. If you have any point, if you have any point, like here, that point in orange here, and you draw the tangent line, you can see that this linear function, the slope is negative because the line is going down. So this means that the interval from 0.8 all the way down to 2 is an interval where f prime is negative. And then after 2, so from 2 to infinity, the graph is going up again. So I have another example of a point. I think I forgot to mention it, but between -1 and 0.8, I just drew an example for all of them where you can see that the slope of the tangent line is positive because the line is going up. So the last interval here, is going to be 2 to infinity. And on that interval, pick any point, the slope of the tangent line is strictly positive. So this new definition, I just want to end that section with this very important remark. So this new definition of slope of the tangent line. So you should be able, if I give you a function defined visually by a graph, you should be able to tell me on the graph where is f prime positive, where is f prime negative, where is f prime 0, and where is f prime undefined or does not exist. So visual ideas again. So with a graph, there's a lot of things you can tell me now. But again, the big plus of f prime, and this will start in the next section, is that this is something that we can compute. If you have a function that is given by a formula, you can compute f prime. So you can get a formula for f prime. And that's the beauty behind it. But anyways, for now, for those two sections, still in the realm of visual stuff, that's it. That's all. Bye-bye.